Okay, so I want to find the arc length of the cardioid r equals 1 plus cosine theta. I think this was the function that we were working with before, but if not, let's just do this one. And what we did is we used the arc length formula. We're going to integrate from 0 to 2 pi, because those are the bounds that we need for the cardioid. We have the square root of r squared plus dr d theta squared. So r is 1 plus cosine theta, so we get that squared, plus the derivative of r with respect to theta, so that's going to be negative sine theta squared, d theta. And then if we simplify, this is going to be the integral from 0 to 2 pi of the square root of 1 plus 2 cosine theta plus cosine squared theta plus sine squared theta. And cosine squared plus sine squared theta is just 1, so this is really the integral from 0 to 2 pi of 2 plus 2 cosine theta. And we're just going to evaluate from 0 to 2 pi. Okay, and so what we did is we remembered that we've actually seen this before, but 2 plus 2 cosine theta is 4 cosine squared theta. This comes from the fact that we have the reduction formula for cosine squared theta is 1 plus cosine of 2 theta over 2. So actually I'm slightly lying to you here. 2 plus 2 cosine theta was, but let's just derive it. It was 4 cosine squared of theta over 2. But this tells us that 2 cosine squared theta is 1 plus cosine of 2 theta. And then we have a 2 plus 2 cosine theta, so I'm going to multiply both sides by 2 again. 4 cosine squared of theta is 2 plus 2 cosine of 2 theta. Our 2 theta that we have here, I'm sorry, I'm confusing variables here. What I have is fine. Let's just change our thetas to x's, just so it's a little bit easier to see what's going on here, just in case there's any confusion there. So this is 1 plus cosine of 2x over 2. And so 4 cosine squared of x is 2 plus 2 cosine of 2x. Our 2x is theta, and therefore x is theta over 2. So this is going to be the integral from 0 to 2 pi of the square root of 4 cosine squared of theta over 2. Because to go from the right side to the left, the angle in cosine has to be halved. So we go from 2x to x. So if we start with theta, we have to go to theta over 2. Okay, that's the rationale there. And now what we're going to do is we're going to evaluate this integral. This is a square under a square root. So this is going to be the integral from 0 to 2 pi. And I made the ridiculous error in class of saying that the square root of something squared was just that thing, but it's not. It's the absolute value. So this is 2 cosine of theta over 2, integrated from 0 to 2 pi. And there's 2 ways that you could do this. You could kind of just think about symmetry. And so if you break this up into the integral from 0 to pi, and then from pi to 2 pi, you're going to see that the 2 integrals are going to be equal just by symmetry of cosine. So what I mean by that, let me just explain a little bit. If we think about cosine, let's say y equals cosine of theta, or cosine of x, it doesn't matter. So let's look at y equals cosine of, say, x over 2. And we're going to go from 0 to 2 pi. And so think about how this is going to work. If x goes from 0 to 2 pi, then x over 2 goes from 0 to pi. And so this curve is going to be kind of a really stretched out cosine curve. And so at pi, the value would be 0. And then from pi to 2 pi, that's going to be the same value, except this is y equals cosine of x over 2. And so if I take the absolute value, what's going to happen is that this curve is going to get reflected above the x-axis, and therefore the integral of this function and this function are going to be equal. And so that's one way that we can deal with this. So this is going to be the integral from 0 to pi of 2 cosine of theta over 2 d theta. And then the other piece is going to be that same value, so 2. That symmetry is actually what got us in trouble if you think about it, because I just forgot the absolute value, and then I found this area, added up with this area, and we got 0. So the fact that these are the same, we actually already knew. So that's one way to deal with it. Another way to deal with it, if you didn't like that symmetry argument, is you can break this up into the integral from 0 to pi. So we have 2 cosine theta over 2 d theta, plus the integral from pi to 2 pi of the absolute value of 2 cosine theta over 2. And the function's going to be positive in the first half, so it's the integral from 0 to pi of 2 cosine of theta over 2. It's going to be negative in the second half, so it's going to be negative 2 cosine of theta over 2 from pi to 2 pi. And you'll see that you'll get the same answer. I'm just going to use the symmetry argument since we've already written that out. So this is going to be 4 times cosine of theta over 2. And if we integrate cosine of theta over 2, we get 2 sine of theta over 2. And we evaluate that from 0 to pi. And so that's going to be 8 times sine of pi over 2 minus sine of 0. And so we get that the arc length was 8. Okay, and so that's how that's going to work. So here, if we did it this way, we would end up with, when you write in these integrals, you would get 4 plus 4. So these really are going to be, by symmetry, these areas are going to be the same, and you still get 8. Okay, so that's how that would work. The last thing that I want to do in this video here is I want to look at the curve, say r equals f of theta, and I want to think about derivatives. And we talked about this a little bit, but we didn't actually practice with any of these. So I want to think about, let's just do this concretely. Let's take r equals 1 plus sine theta. And we're going to go from 0 to 2 pi. And what I want to do is I want to compute the derivative of the curve, so dy dx. So we've written this in polar, r equals f of theta. Well, I want to find the derivative of y with respect to x, so that's still the slope of the tangent line. And the way that we have to do this is we have to do two things here. We're going to use the parametric equations formula that we know. So we have dy d theta over dx d theta. But then also we have to think about what's the derivative of y with respect to theta and the derivative of x with respect to theta. And here we remember that x is r cosine theta, y is r sine theta, and our r is 1 plus sine theta. So we get 1 plus sine theta times cosine theta for x and 1 plus sine theta times sine theta for y. And then what we're going to do is we're just going to differentiate each term here. And let's compute the derivative, and then after we compute the derivative, let's find all the values theta where the curve r equals 1 plus sine theta has a vertical or horizontal tangent line. Okay, so it has a vertical or horizontal tangent line. All right, so that's our goal. And now we need to get to work. So our y is, we're going to be differentiating, let's write it one more time. Our y is sine theta plus sine squared theta. Our x is cosine theta plus sine theta cosine theta. And so if we take dy d theta, if we differentiate, we're going to end up with cosine theta plus 2 sine theta cosine theta. Dx d theta is going to be negative sine theta plus, we'll need the product rule, so the derivative of sine theta times cosine theta is cosine squared, plus the derivative of cosine times sine, so minus sine squared theta. Okay, and so that's our derivative, and then we want to find all the values where we have a vertical or horizontal tangent line. So the horizontal tangent line is going to be the easiest to find. So that's going to be when the numerator of the derivative is 0. So it's going to be when cosine of theta plus 2 sine theta cosine theta is 0. So that implies either cosine of theta is 0 or 1 plus 2 sine theta is 0. So that's when cosine of theta is 0 or sine of theta is negative 1/2. And so cosine of theta being 0 happens when theta is pi over 2 and 3 pi over 2. Okay. And sine of theta being negative 1/2 happens when theta is 7 pi, I think we talked about this one in class, but 7 pi over 6 and 11 pi over 6. So those are the values where I'll have a horizontal tangent line. Okay, and now we need to think about now we need to think about when we're going to have a vertical tangent line. So a vertical tangent line, that's going to happen when the derivative of our denominator is 0. So that's going to happen when negative sine theta plus cosine squared theta minus sine squared theta is 0. And so let's see, how could we do this? One way is I'm going to add the sine terms over. So we get cosine squared is equal to sine squared plus sine. And then we can change, that's just sine to the first. And then we can change cosine to be 1 minus sine squared. So that's going to happen when 1 minus sine squared is equal to sine squared plus sine theta. And then that happens when, 2 sine squared theta plus sine theta minus 1 is equal to 0. And so that factors as 2 sine theta and sine theta and 1 and 1. And then we just have to be careful about the signs here. So this is a plus sine theta, so the 2 should be positive. So this is going to happen when theta is equal to, so when sine theta is equal to 1/2, or when sine of theta is equal to negative 1. And so that happens when theta is pi over 6 and 5 pi over 6. And when, sine of theta being negative 1 happens at 3 pi over 2. Okay, and so that's when we're going to have a vertical and horizontal tangent line. Okay, and so that's how we would do this. It's basically the same idea. You find the derivative, you take the numerator, set it equal to 0, that gives you the horizontal tangent lines. You take the denominator, you set it equal to 0, that gives you the vertical tangent lines, and then we can kind of go from there. Okay, but that's how that works in practice.